Hi, today we will look into the knuckle joint design. This is the picture of Don Bosco. This is the picture of Miss Alfonsa Lona Colangeri. Let us look into the question. It is required to design a knuckle joint for the robotic arm used in the automobile industry subjected to an axial tensile force 70 kilonewton. This is the picture of the knuckle joint. As you can see, here you have the fork end and here you have the eye. The eye is further connected to another eye, and here you can see the fork is connected to another fork. So we will be designing this particular part. Let us take a simplified version of the knuckle joint. These are the parts for the knuckle joint. We have a rod. Rod consists in the fork as well as in the eye end. A knuckle pin there is. This connects the fork and the eye. The single eye looks in this manner. We have double eye, and this is also called as the fork. These are some of the parts in the knuckle joint. The assembly of the knuckle joint consists of something like this, where the single eye comes and mates with the double eye. The single eye leaf looks like this, whereas the double eye has two leaves. The single eye is placed in between the leaf of the double eye. After this, the knuckle pin passes through the double eye and the single eye. Hence, we form the assembly of the knuckle joint. It's a very simple assembly and it is easy to manufacture. And you can observe the knuckle joint in many joints nearby. Let us look into the knuckle joint tree diagram. In the knuckle joint, it consists of a rod which is subjected to a tensile stress. The knuckle pin is subjected to shear, crushing and bending stress. The single eye is subjected to crushing, shear and tensile stress. Double eye consisting of crushing, shear and tensile stress. It consists of split pin and some accessories. Let us look into the assembly diagram of the knuckle joint. Here you can see the double eye and the single eye, and through which the pin passes through. Here D1 is the diameter of the knuckle pin, whereas D2 is the diameter of the knuckle pin head. D3 outer diameter of the leaf of the fork as well as eye. Knuckle joint is subjected to load of P. Here you have thickness T for the eye end and thickness T1 for the double eye end. This is the front view we have, and here we have the top view. The dimensions are defined in this manner. So these are some of the critical parameters with respect to the knuckle joint. Let us look into the free body diagram of the knuckle joint. The knuckle joint is designed with respect to the free body diagram. The free body diagram is constructed using the principle that actions and reactions are equal and opposite. The sum of all horizontal forces acting on individual parts must be equal to 0. Here in the figure you can see there is an applied force P, and because of this applied force P on the double eye, you can see a induced force P by 2 here above and P by 2 below is induced. Total force acting on the double eye is cancelling out each other, whereas on the left hand side you can see P, and here if you add this P by 2 and this P by 2, the horizontal forces become 0 on the double eye. On the eye end, one can observe that external applied force P is applied. The reaction force for this is the applied force P here, which is opposite in direction. Now, this is how the horizontal forces on the single eye is equal to 0. Now, because of this particular force on the single eye, onto the knuckle pin there is again an opposite equal force P which is acting on the knuckle pin. And now you can see on the right hand side there is a force P by 2 and P by 2. These two forces are due to the leaves of the double eye. And you can see on the double eye we have a force like this in this direction P by 2 and in this direction P by 2. At the same time you can see an opposite force P by 2 on the knuckle pin in this direction, as well as you can see P by 2 force in this direction. Both the directions are opposite and the magnitude are equal, and that's why the horizontal forces on the knuckle pin is equal to 0. Hence, we have understood the forces on the knuckle joint. Let us look into the assumptions of the knuckle joint. The rods are subjected to axial tensile force. The material is homogeneous, isentropic, and obeys the Hooke's law. The effect of stress concentration due to slot steps are neglected. The force is uniformly distributed in various parts. Now, the material assigned to all the parts, let us assume it to be same. So we have taken plain carbon steel C40 as the material, and the yield tensile strength for that is 33 kgf per mm square with reference to design data book PSG page number 1.9. We have selected this material because this material is easily available in the factory. Now let us convert this SYT in terms of Newton per mm square. So this becomes 330 Newton per mm square. Assume the same factor of safety for all the parts with respect to the knuckle joint. We can see that for direct axial load, the factor of safety is taken as 2 when it is a dead load. This is with reference to VM fares as given in PSG page number 1.43. Hence, for a direct axial load, we have taken factor of safety as 2. An additional factor is taken to accommodate stress concentration factor, that is 1. So when we add this, the final factor of safety becomes 3. Design stresses with respect to the material C40 can be taken in the following manner. Design sigma T is equivalent to design sigma B, which can be SYT upon factor of safety, that comes around 110 Newton per mm square. Design tau is equal to design sigma T by 2, so that comes around 55 Newton per mm square, and design sigma CR is equal to design sigma T multiplied by 1.3, so it comes around 143 Newton per mm square. Let us start the design. When we design the rod part is present with respect to the double eye as well as with respect to the single eye with the same dimension, that is the D diameter. So when we apply tensile stress, it can break something like this as seen here with respect to the single eye, and the cross section will look something like this with the diameter D. So induced sigma T is equal to P upon pi by 4 D square less than equal to design sigma T. When we put up the values, we can find out D as 28.46 mm, which can be approximated to 29 mm. The design of knuckle pin consists of shear stress. So that because of the direct shear stress, as you can look into this figure, at this particular section as well as this particular section, you can see the pin gets broken in two halves. Hence, this is a case of double shear, and that's why in the formula you can see the value 2 here, because there is area 1 here and area 2 here. This is a double shear condition, and the diameter of the pin, as you can see here, is given as d1. So we are putting it pi by 4 d1 square. So we can see that d1 is the diameter of the knuckle pin, and hence we can put up the values into the formula, where p is 70 into 10 raised to 3, design tau is 55, and we can find the value of d1. Here d1 value comes around 28.46 mm, which can be approximated as 29 mm. Here, let us look into the crushing stress induced in the knuckle pin due to the single eye end. We can see that the knuckle pin picture is given here, and whenever we consider the induced crushing stress, the area considered is always projected area. Since the whole cylinder is subjected to the crushing stress, the projected area will appear like a rectangle and the area is d1 into T. Hence, in this particular equation, we know what is the value of P, we know what is the value of D1, and design sigma CR, we know the value. So, by this formula, we can find out the thickness T of the knuckle pin. So, let us place in the values, the known values after substitution. We get the T value as 16.87 mm, which can be approximated as 17 mm. Now, using empirical relation, we can say that thickness of the single eye T is equal to 1.4 times D, and therefore T becomes around 40.6 mm, which can be approximated as 41 mm. So by experience, they have said that T value should not be 17 mm, which is very less, but approximated to 41 mm, which is quite safe value and which depends upon the experience of the designer. We also have another empirical relation for T1. T1 is equal to T by 2, which can be calculated as 20.5 and approximated as 21 mm. Here, T1 is the thickness of the double eye. Let us study the bending stress induced in the knuckle pin. Bending happens due to the opposite forces acting on the knuckle pin with respect to the single eye and the double eye. The bending analysis of knuckle pin is considered as a simply supported beam with uniformly distributed load acting in the middle portion due to single eye and uniformly varying load acting in the remaining end portion due to double eye. In this figure you can see we have the knuckle pin and we have the single eye. The force P acting on the single eye is repelled by the knuckle pin in the form of uniformly distributed load in the middle portion, and the force P by 2 applied by the double eye is showed by uniformly varying load at this particular end at the knuckle pin. Hence you can see the uniformly varying load and distributed load as shown in this figure. Let us understand the bending stress induced in the knuckle pin. When considering forces in bending stress in symmetric body, only half of the section of the body is considered. That is, forces acting on half the section will be considered. The second point is, the distance between the force and the central line is considered. Third point is, the forces intend to revolve towards the center of the body with respect to the cotter pin. Let us see here, for a triangular load distribution UVL, the center of the gravity of the resultant load is at a distance of T1 by 3 from the wall. Let us look into the figure, and this is the uniformly varying load which has a length of T1 distance. Now here we have a wall. The force is acting at the center of gravity of the resultant load at a distance of x from the wall. This x distance will be always T1 by 3. So this is a point that is to be understood. Let us look into the uniformly distributed load UDL. The center of gravity of the resultant load is a distance of T by 4 from the neutral axis. When you look into the figure, this line is the neutral axis, the central line, and you can see the uniformly distributed load at the upper section and the lower section. Only one section we consider. So when we look into the upper section, you can see this is the point load that is acting at a distance of x. So this x distance will be always T by 4. So this is another point we should be considering. Here, one can observe that the uniformly distributed load is divided into two sections. This is the upper section and this is the lower section. The length of the uniformly distributed load at the upper section is given as T by 2. In the bending stress, we will be only considering the upper section. Now, the uniformly distributed load can be converted into point load as shown in this figure. So the point load is acting at the distance of T by 4 from the neutral axis, and the magnitude of the point load is P by 2. You can also see that P by 2 load is acting at the bottom section also with the distance T by 4. One can also observe that on the right hand side, we have the uniformly varying load. This uniformly varying load can be converted into the point load. The point load is acting at a distance of x from this particular line, which is also called as the wall. So this particular distance x is given as T1 by 3 and the magnitude of the force is P by 2. You can see similar arrangements in the bottom section where the force with the magnitude P by 2 is acting at the distance of x. One can also observe that the distance between the neutral axis and the wall is given by T by 2. Once we have understood this diagram, we can find out the maximum moment that is acting on this particular body. To find out maximum movement, we know that we have to consider these forces are trying to revolve at the center of the spin. So let us take the force that is situated at the top, where P by 2 force is acting at a distance of x plus T by 2. So we know that the force is P by 2 and we know T by 2 plus x. X is equal to T1 by 3 as shown here. So we have found out the forces and their distance on the right hand side. We can say that this force at the right hand side and the other force at the left hand side are opposite to each other. Therefore, we are considering a minus sign and considering the force on the left hand side. The left hand side, the force is P by 2, which is acting at the distance of T by 4. So that is what we have represented here. Hence, from this particular diagram, we have obtained the maximum moment acting on the knuckle pin. Now, we have this many formulas with us, whereas maximum moment is found out by this formula from the figure, where we have the area moment of inertia with respect to y as pi into d1 raised to 4 upon 64. This is particular for the circular section as given in the PSG 6.1. Can find out the distance of the maximum fiber from the neutral axis as d1 by 2. So y is equal to d1 by 2. This is the distance of the outermost fiber to the neutral axis. The bending stress induced in the knuckle pin due to single eye and double eye can be calculated. In this particular formula, we know the value of mx, we know the value of design sigma t, and we can substitute the value of y and iyy. In this particular equation, d1 is unknown, where d1 is the diameter of the knuckle pin. After substitution, diameter d1 comes around 39 mm approximately. Now we can observe that we have got the diameter d1 is equal to 29 mm from the direct shear stress induced in the knuckle pin due to single eye and double eye. We have also calculated d1 as 39 mm with respect to bending stress induced in the knuckle pin. Hence, we have values from two different stresses. We will be selecting the higher value. Hence, the final dimension of d1 is 39 mm.
The direct shear stress induced in the double eye due to knuckle pin. In this figure, one can observe that the knuckle pin is mating with the double eye. The knuckle pin is pulled in this direction and the double eye is pulled in that direction. Because they are pulled in opposite direction, two sections of the double eye gets sheared off as seen in this diagram from this particular location. Now the shaded area is shown in the blue color as seen here. Now these are the shared area which got broken off from the double eye. Here T1 is known as the thickness of the single leaf. In both the leaves, thickness is T1. Now we are interested in these sections. Let us assume that the portion, here you have the sheared portion above and below. Here also we have sheared portion above and below. For the two sections we have above and below portions. Let us assume that the shaded portion have same and equal area. So we are interested to find out this area. One parameter is known here, that is T1, because the thickness of the leaf is T1. So this parameter is T1. To understand and find out the other parameter, we have to look into this figure. In this figure, one can observe that the outer diameter is given by D3 and the inner diameter here is given by D1. And if we want to find out the half the diameter of the outer circle, it is given by d3 by 2, and half the diameter of the inner circle is d1 by 2. Now the red area is the break line, and this particular line we are interested to find out the length of this line. So the length of this line can be found out as d3 by 2 minus d1 by 2. So this will give me the length of this particular red colored line. And to find out the area of this shaded portion, I can say that T1 multiplied by d3 by 2 minus d1 by 2 will give me the area of the shaded portion. Now let us look into the induced tau. The induced tau is equal to P upon area. Now we have found out the area of the shaded portion, so we have written that. That is d3 minus d1 upon 2 multiplied by t1. The first 2 here stands for double share. Each section has above and below area, and that's why we call it a case of double share. So a 2 number is given for that. Now the rare 2 is for 2 leaves. We have leaf number 1 and leaf number 2, and that is the reason we have given 2 here. Now in this condition we have found out induced tau and its formula. Now we can put the known values and find out the unknown values. We have substituted the known values, and the unknown parameter is d3. After substituting all the values and equating it with equal to 55, the d3 value comes around 69.3 mm, which can be approximated as 70 mm.
For other designs, refer to the link provided in the description. Let us look into the tensile stress induced in the double eye due to the knuckle pin. Here, the double eye is mating with the knuckle pin, and a tensile force is induced in the left hand side of the pin, and a tensile force is induced in the right hand side of the double eye. Because of these tensile forces, the double eye divides itself into two parts. As you can see, this is one part and that is the another part. The shaded area is the area under consideration. So the shaded area is shown in this 2D diagram. One can observe this is how the tensile failure takes place due to the tensile stress in the double eye. Let us look into the calculation. Here the digit 2 is shown for the two leaves. This is leaf number 1 and this is leaf number 2. Now the shaded area can be given as d3 minus d1 multiplied by thickness, which is t1. In this manner we can find out the shaded area and the formula for the tensile stress. Let us put in all the known values into the equation and find out the induced tensile stress. The induced tensile stress is 53.76, which is quite lesser than the design tensile stress. Hence, this section is safe. Let us look into the crushing stress induced in the double eye due to the knuckle pin. In this figure, we can observe that the double eye is being mated with the knuckle pin. The knuckle pin is being pulled to one side and the double eye is pulled to the other side. Because of this, the failure of the double eye occurs. One can observe that the inner area is the crushed area, which is also the circumferential area. In the crushing stress, the circumferential area is converted into the projected area. The projected area appears like a rectangle, and this shaded area is the crushing area. Hence, in this manner, the failure of the double eye due to crushing stress occurs. Let us look into the formula. The two leaf of the double eye indicates the 2 digit here. Hence, there are 2 leaves, so we have multiplied by 2. The area is d1 multiplied by t1. This is the shaded area. Hence, we have d1 multiplied by t1 in the denominator. Hence, this is the formula and we can put values and find out. After putting the values in the crushing stress, we can find out the induced crushing stress as 42.73, which is quite less in magnitude with respect to the design crushing stress, which is 143. Hence, we can say that this particular section is safe. Let us consider the direct shear stress induced in the single eye due to the knuckle. Here one can observe that this particular eye end is mated with the knuckle pin, and because of the forces acting on it, this particular section of the single eye get sheared off. We can see this nicely in the 2D figure. In the 2D figure you can see the shared area 1 and the shared area 2. The small section gets sheared off. This particular section has two areas as shown in this figure. Hence, a digit 2 is multiplied, which indicates a double shear. The length of sheared area can be said as d3 minus d1 upon 2, since it is half the diameter, and the thickness of the single eye is given as t. Hence, we have obtained the formula for the shear stress. Let us put in the values. After putting up the values, we can see that the magnitude of the shear stress is slightly more than the design tau value. This minor differences in the value can be neglected. Hence, we can say that this particular section is safe. Let us look into the tensile stress induced in the single eye due to knuckle pin. In the 3D figure, one can observe that due to the forces acting on the knuckle pin and the single eye, the double eye gets divided into two halves. The shaded area is the stressed area. In this 2D figure, one can observe that T is the thickness of the single eye, and D3 is the outer diameter of the single eye, and D1 is the inner diameter of the single eye. Let us derive the formula. The shaded area here can be derived as D3 minus D1 multiplied by T. So we get the shaded area. The shaded area is the tensile area. After putting in the values, one can observe that the induced tensile stress is 55.07 Newton per mm square, which is quite less than the design tensile stress. Hence, the section is safe in tensile stress. Let us look into the crushing stress induced in the single eye due to the knuckle pin. Here we can see that the single eye and the knuckle pin are mating each other, and due to the forces, the inner surface of the single eye gets stressed. The inner surface is the circumferential area. One can see that in crushing stress, the circumferential area is converted into projected area. Here, the projected area looks like a rectangle. This rectangle is the crushing area. Hence, due to the crushing stress, the failure happens in the following manner. Let us put in the values and find out the induced crushing stress. After putting up the known values, the induced crushing stress comes around 43.77 Newton per mm square, which is quite less than the design crushing stress. Hence, the section is safe. Design of the split pin. The design of the split pin moreover depends upon the experiential basis. Let us select the material as stainless steel, and the diameter of the split pin can be somewhere between 6 to 8 mm. Let us assume it to be 6 mm. Let us look into the dimensions of the knuckle pin. Diameter of the pinhead is represented as dh. dh is 1.5 times the diameter of the rod. After putting up the values, we get it as 43.5 mm. Thickness of the pinhead is given as tph. Assume it to be 10 mm. The length of the knuckle pin depends upon the thickness of the single eye and the thickness of the double eye, and added some margin. After putting up the values, the length of the knuckle pin comes around 93 mm. At this point, we can say that we have completed the design. The following references were used for the design. This can be useful for the further study.